Assalamualaikum warahmatullahi ta'ala wabarakatuh and salam sejahtera. Okay, today lecture we're going to continue with our current topic, which is regarding magnetostatic. So Alhamdulillah, we have completed the first task under the field of magnetostatic, which is Bio-Savat. So now we're going to the second task stated in our course outline, which is application of the Ampere Circuital law, okay, in calculating magnetic field intensity for symmetric current distribution. So that's going to be our concern in this particular video session. We're going to talk about Ampere Circuital law. So that should be our objective here. Okay, so hope you're clear with that. So let's continue. So the issue that we're going to discuss is Ampere Circuital law. Okay, that should be our concern. So for those who still want to refer to our textbook, so please refer to section 7.3, page number 302. Okay, that should be relevant to what we're going to discuss in this lecture. So this is referred to our textbook. So what is ACL for us? Remember, when we learn magnetostatic, actually we are repeating what we have seen in the electrostatic domain. So magnetostatic is just a repetition of electrostatic. So as what we have seen before when we talk about Bio-Savat, it's similar to what we have seen in electrostatic known as Coulomb's law. So now what we're going to go now, we're going to talk about ACL. For sure it's going to be quite similar to Gauss' law. So that's proof it. Okay, but for me, what is ACL? Very simple. First thing for me, ACL is alternative to Bio-Savat law. So that should be the first thing always in my mind when I talk about Ampere Circuital law. So it's an alternative, meaning that we can still find magnetic field, okay, using ACL as well as Bio-Savat. Similar, we can find electric field by adopting either Coulomb's law or Gauss' law. So in our case here, Ampere Circuital law is an alternative to Bio-Savat law. So, and the second point that's very important, for us to be able to use ACL, the source, which is current, must be infinitely large. So therefore, I'm going to state here only applicable for infinite current source. Applicable to infinite current source. So therefore, our current source can be what? Line, good. What else? Surface or volume. So therefore, all these three current sources, if they are infinitely large, we can use ACL to find the magnetic field. Okay. And number three, what I'm going to remind myself, steps in solving ACL are similar to Gauss' law. Okay, so the steps here are similar to Gauss' law, meaning that we have seen there are systematic way that we have selected when we solve Gauss' law. So we're going to see the same steps going to be adopted in our ACL approach here. Okay, so that's what we're going to do. I'm not going to discuss the theory, because the theory you can refer by yourself from our textbook, but anyway, when we solve the problem that we're going to introduce later on, we can relate to the theory behind Ampere's circuital law. So what I'm going to do now, I'm going to solve problem based on what we have seen before, specifically referred to the problem that we solved under the category of Biot-Savart. So let's recall the first problem that we did together. See, anyone can recall? So recall, so example 1. So let's recall example 1. Okay. So I'm going to put recall Biot-Savart. So meaning that the problem that we're going to solve together now will be exactly the same as what we have seen in Biot-Savart. We call it example 1. So what's example 1? Anyone can remember the problem all about? Okay, so the problem asks us to do what in example 1? Find H due to finite line current, correct? That should be example 1 of our Biot-Savart law that we solved together. So, and then what we obtain, the solutions that we obtain is what? The solution that we obtain for finite line current is H equal to phi. Remember, so just copy the solution. I divide with 4 pi r bracket sine alpha 1 plus sine alpha 2, correct? And then we must use this equation together with the graphical representation of the problem. What is it? So we should have the current source given as this. So the current source is the red color line, where we assume the current flowing upwards. Then we want to find our H located at this position. Then we have to draw the triangle. The first thing that we must be able to determine this R. What does this R appear to be in our graphical representation? Going to be this blue line. And then this line must make an angle 90 degrees to the line current. So this is our R. Then what we want to define later on, alpha 1. What is alpha 1? The angle shown here. So this is our alpha 1. Then what is alpha 2, which is the angle up here. So this is our alpha 2. Okay, that's what we obtain using Biot-Savart for finite line current. Then we extend the solution for infinite line current. So our solutions become what? Okay, H will be equal to what? Phi, I'm just using the above equation in my problem solving here. I divide with, yes, 2 pi r, where we are stated that alpha 1 equal to alpha 2 equal to 90 degrees. Okay, that's what we have proved together using Biot-Savart. Yeah. So now, so as you can see, infinite is our main focus now. Why? Because that should be related to the characteristic of current source that we can use ACL as the approach to find field. So therefore, I'm going to solve this problem, okay, infinite line current, but now we are going to use ACL approach. Hopefully, at the end of our problem solving, we're going to have the same solution as what we obtain using Biot-Savart. Okay, that's going to be our objective now. Yeah? So let's draw our infinite line current. So I'm going to draw it nicely now. So our infinite line current, going to have dotted lines to indicate it's infinite, very, very long. Okay. Okay, so now I'm going to show the current flow as similar to the one that we shown before, flowing upward. I'm going to add coordinate now just to make our problem a bit easier to follow. So I'm going to set this going to be my z-axis. Okay, this particular axis is our x, and this is going to be our y. Okay, so let's write a bit now. Okay, so find h using Ampere Circuital law method. So this is our question, because it's infinite, minus infinity up to infinity. Okay, so we want to find h using ACL. Okay, this is our objective now, to find h due to our current line current, which is infinite now, but specifically using Ampere Circuital law. Why? Because Ampere Circuital law can be used when we are dealing with infinite line current. Okay, so remember point number 3, when we want to solve ACL, the steps are similar to Gauss law. So what should be the first thing we must decide when we want to solve problem using Gauss law? Okay, so we just revise ourselves now. Yes, what should be the first step that we should use? Good, we're going to choose the proper coordinate system. So what should be the coordinate system we're going to adopt in this particular problem solving? Good, cylindrical. Okay, that should be the first step we're going to do in ACL. Okay, the second step should be determine the location of H. Okay, I'm going to put here location of H. Okay, so where is it, our location? Let's say here. Okay, it's quite similar to the one that we did when we solved Gauss law before. So here. Okay, so what is it? This is our location of H. So this location of H. Okay, number 3. Okay, in Gauss law, we must build a Gaussian profile. Remember, Gaussian profile is a structure that completely closed, and then that particular surface must pass through the point of interest. Okay, in our case before, point of interest is D, but now using a similar method, we're going to determine or build Amperian loop. Okay, Amperian loop. So I'm going to underline. So Amperian loop is similar concept to Gaussian profile. Okay, for Gauss law, the sensor is a completely closed surface, whereby in ACL, our sensor is completely closed loop. Okay, it's not a surface anymore, it's a loop, it's a line. So therefore, we call that Amperian loop. So for me, in order to draw a proper Amperian loop, I always ensure that my current drawn in this particular step will be in 2-dimensional. Okay, what does it mean? I'm going to determine the way of the current going to be shown here, either coming out from my paper or going into the paper. So in this case, I'm going to choose that my current drawn to be coming out from my paper. So let's draw it now. So my current here is coming out. Okay, it's a dot. So therefore, I'm going to put axis now. because the axis should be x-axis, y-axis, correct? Okay, that should be my structure, my diagram. Okay, so we are changing from 3D problem into 2D representation, where we purposely choose the current either coming out from the paper or going into the paper. So in this case, I'm choosing to be coming out, so it's a dot. Actually, it's a line, but seen from the top, from this position, that current appears to be a dot. So the current having magnitude I. And where is my location of H? Let's say my location of H to be at this position. So I'm going to put H here. Okay, so therefore I'm going to draw my loop. So the loop must be selected to be agreeable to the coordinate system that we choose. So we already chosen the coordinate to be cylindrical. So my loop now going to be a circle. Okay, where the center of the loop is coinciding with the position of the current. And then I'm going to determine that this particular radius of the loop is given as R. General representation. Why? Because this point H is not fixed. It can be anywhere surrounding our current source. Therefore, the loop will always follow the position of H. If I move the H to be this location, I'm going to redraw my Ampere loop to pass through that location. As you can see, it's a sensor. The idea is similar to Gaussian profile, where you can move the surface according to the position of the electric field. In this case, I can move the loop according to the position of the magnetic field. Okay, so that should be step number 3. Yeah? Building proper Amperian loop. How I do it? Redraw the problem such that the current going to be shown as only coming out or going into. Then I'm going to draw the loop based on my selected coordinate system that I choose earlier. Therefore, so now step number 4, solve Ampere's circuital law equation. What does it say? It said that H dot dl should be equal to I enclosed. This is the standard ACL equation. H dot dl equal to I enclosed. It's quite similar to D dot ds equal to Q enclosed in Gauss law. Okay. So how are we going to solve this mathematics? By relating the mathematics to our structure. I mean by that, the left-hand side of this equation must be related to the shape of the loop, whereby the I enclosed going to be defined based on the current inside the loop. Okay, that's how we relate the equation to our schematic diagram that we have built under the step number 3. Okay, so I'm going to state this equation to be left-hand side and right-hand side. So easier for me to relate it later on. So let's do that now. Okay, so I'm going to do the left-hand side first. Left-hand side. Okay, so this part now, so it's equal to integration of H dot dl only. I'm going to focus on that particular part of the equation. Remember, the way we're going to define this equation must refer to the diagram. So, I'm going to substitute now. Okay, integration going to be there. Okay, how about the H? What should be the H appear to be at this position? At this particular junction, I'm not sure. Therefore, I'm going to represent the H as in general representation based on which coordinate? Cylindrical. Okay, so therefore my H now consists of H R in R direction plus h phi in phi direction plus hz in z direction. Why? Because we are using cylindrical coordinate, consists of component r, component phi, and component z. So that should be our general substitution for our h at this particular point. Now, dot. Okay, the dl must be based on the sample of the loop. Okay, that should be our dl. What should be the dl represented here? And we must refer back to our table number, I think of table 2 if not mistaken, okay, of the week number 1 that we built together. Okay, what should be the dl mathematics here? Okay, good, should be r d phi in which particular direction? Because dl is a vector. Yes, phi directions. Okay, that should be the substitution now. Yeah. Okay, so therefore the dl should be r d phi in phi directions, because the dl must represent our dl on the diagram, and based on our table that we built together, that particular term should be substituted as this substitution. Okay, now let's continue. So I'm going to solve the mathematics now. So it's just a dot product now. R direction dot with phi direction, what going to be my solution? Good, 0. Yeah. Phi direction dot with phi directions, yes, 1. Z unit vector dot with phi unit vector, yes, 0. So my final solution will only consist of integration of h phi r d phi. Okay, because the phi dot phi only going to be the final component appear in the mathematics, whereby the r dot phi going to be 0, the z dot phi also going to be 0, and therefore what should be our limit? Since it's a complete circle, should be 0 to 2 pi. Okay, then our final solution here going to be 2 pi r h phi. Okay, that should be the solution for left hand side. Yeah, 2 pi r h phi. Now, so let's continue now with our right hand side. The right hand side should be I enclosed. Okay, based on our observation now, nothing extraordinary what we can observe from this simple diagram. What should be the total current passing through this loop? Yes, it's I. Correct? Because only I that passing through this loop. There's nothing else than that, only I. So therefore, I'm going to say that the I enclosed must be equal to I. Okay, so what we have obtained, solution for the left hand side, solution for the right hand side. So let's relate them together. Left hand side equal to right hand side, so 2 pi r h phi must be equal to I. And then our objective to find what here? To find h. Okay, so now what should be my h? Okay, my h now, okay, should be equal to, remember we are solving this part of mathematics, should be I divided with 2 pi r in phi directions. Okay, so let's compare with our previous solution obtained by Bio-Savant. Do they appear to be the same? Alhamdulillah, they are to be the same. So that should be our steps using ACL. So we have verified that our solution here does agree with what we obtained using Bio-Savant. So indicate to us the method shown here is proper method. So let's recall what we need to do in ACL. Remember the steps similar to Gauss law, as what we have done in Gauss law. We choose the proper coordinate system. Then we determine where should be the location of field that we want to determine. Then we build the appropriate sensor. Then we solve the appropriate mathematical equations. And then we got, inshallah, the solutions. Okay, so let's go. Okay, so let's do something a bit extraordinary now. Okay, still referring to our infinite line current here, but now what we're going to do, we're going to zoom in. Okay, I'm going to zoom in, Z-O-O-M, in. So we're going to zoom in. From far away, we going to see this particular current appear to be as a line. So if we move closer to this line current going to change itself to becoming a volume current. So let's do that now. Example number 2. Okay, example number 2. So we have not solved this problem using Biosavant because using Biosavant, subhanallah, is a complicated method. So therefore, I'm going to show this problem can be solved very easily using Ampere Circuital law. So given now what we have now, so our line current now change itself to be a volume current. Okay, that's what it's going to do now. So it's a part of the volume current. So it's a cylinder now. From far away, it appears to be a line. When we move closer, the line now changing to a cylinder. So since this is part of infinite line current, I'm going to draw dotted line. Okay, so let's give the structure dimension now. So let's say the radius of our conductor is A, because we are zooming in now, you have dimension. And then we already said before, the current now flowing in the cylinder with the total current I. Okay, we're going to put here total current equal to what here? I. Is agreeable to our current flow in the line. So now the current change itself to be the current flowing in that volume, in the cylinder. Okay, so now what we have, a cylindrical structure. Okay, after zooming to the problem that we seen earlier, example 1. So now the question is what? Find H in all region. Okay, find H in all regions. Okay, meaning that we need to determine H inside the conductor or inside the cylinder as well as outside the cylinder. So therefore, H everywhere. So therefore, that's what our objective. Since the structure is infinite, we can use ACL. Okay, so I'm going to use ACL in this problem. So what we need to do now, we need to define, as what we have done in Gauss law, appropriate region. So I'm going to define inside the cylinder as region number 1, outside the cylinder as region number 2. Okay, that's going to be the same step that we have taken in Gauss law. So I'm going to focus first for region number 1. Region 1 only. Okay, that should be our focus now. Okay, so the first thing that we should decide, I think coordinate we have decided earlier, cylindrical, so that coordinate is still applicable for this case. Second, okay, I'm going to determine my H is going to be inside the cylinder because we are focusing in region number 1. Then step number 3, I'm going to redraw the problem in 2D. Remember, okay, we're going to draw such that the current going to be coming out from my piece of paper. So therefore, I'm going to draw now my current to be coming out. So this is from top now. Yeah? Okay, so now the radius is A. And then what we're going to see, there's a lot of current coming out from this structure. Okay, I'm going to draw red color now, indicating there's current all over the places here. So that should be the way I'm going to draw the current. And then the total current flowing inside this conductor is I. Okay, so now, done that, I'm going to show to myself this is going to be my position of H. Okay, done that. So now I'm going to draw my loop, which is a completely closed center at this axis, passing through my H location. So this is going to be our Amperian loop. Okay, and this point H is not fixed. It can be anywhere within region number 1. Therefore, we're going to define the radius to be R. And remember, for region 1, R should be, as what you have done in Gauss law, smaller than A. So therefore, that should be our step now. Okay, so number, okay, position H, draw the loop passing through that point H, and then we define the appropriate dimension, in this case the radius R. Okay, step number 4, H dot dl equal I enclosed. Okay, since we have done for this mathematics before, we can use the previous solution as our solution here, whereby we know that for left hand side going to be H phi multiplied with 2 pi R, yeah? Because it's similar to the one that we did before. So now I'm not going to redo it again, so you can do that in your test or final exam. Just state that equation, well understood. Now I'm going to focus for my I enclosed. Okay, for me to determine I enclosed, I have to decide the I confined by the loop, going to be my shaded black area. As you can see, that's going to be my I enclosed. Even though we know that there's current flow in this region, but we should not consider that in our calculation, because the law state the I must be enclosed by the loop. Okay, that should be my focus. I want to calculate the current in this black shaded region. So what should be my mathematics now? Okay, my current going to be J dot ds. As you can see, if I change the position of my H, the black shaded area going to change as well, and the I enclosed also going to change. Therefore, the current that confined by this loop is affected by the area. Therefore, that's why I multiply with ds. Okay, so therefore, okay, now what should be my mathematics now? Okay, the J here, okay, we call it current density, is the total current divided by total area. Okay, so what should be my total current? My total current should be I, correct? What should be my total area? Pi A squared. Because the total area confined by this cylinder is pi A squared. Therefore, the J should be total current divided by total area. And since it's a vector, so how do I define my direction? So I'm going to give it to be Z directions. Okay, because we already defined based on our axis before, the Z-axis is at the center of this particular structure. Therefore, I'm going to set this to be Z. So let's draw this to be Z-axis. So easier for you to refer. Okay, that's done. My ds now. What should be my ds? Okay, this going back to your table of coordinate system. So I'm going to calculate my ds should be r dr d phi in Z directions. Okay. There. So now let's substitute. So it should be equal to, okay, Z dot Z will end with 1, correct? So I'm going to have double integration. So I'm going to take out first the constant I over pi A squared. Okay, double integrations. Okay. Should be r dr d phi. Okay, so let's choose the limit now. Remember, the limit must only within the shaded black area. So what should be my R range? Yes, 0 to R. Good. Don't choose 0 to A. Cannot be, because in this region, the current still there but not confined by the loop, so it should not be considered. Therefore, we must only consider the current within the Ampere loop, which is the limit up to R. And for the phi, 0 to 2 pi, as what we have did before. Now, what should be our solution now based on this mathematics? Should be I R square over A square, correct? Because this is going to end with pi R square, so the pi cancel. So now what we're going to have now for H1, okay, that's indicate region number 1, should be equal to I R over 2 pi A squared in phi directions. Okay, that should be the solution of our H inside the cylinder, or H in region 1. Okay, so the R and R, that's for only R, 1R, no R square anymore. 2 pi you're going to add, multiply with A squared, so this is going to be the solution for region number 1. Okay, so if you are using Biosavart to solve this problem, subhanallah, it's going to be really complicated and tedious mathematically. Okay, so let's continue now for region number 2. For region number 2, so I'm going to put it here. So this is our region number 2. Okay, what we're going to do the same thing. Current coming out. Okay, this is our A. And then current coming out, I'm going to draw similar to before. Okay. And now our concern to find H in region number 2, which is located here outside. Okay, so what we need to do now? Good, we need to build the loop. The loop is similar as before. Just a circle. And then the radius now, we're going to give it as R. Therefore, it's going to define here R is greater than A. That's going to define region number 2. Okay, that's done. So now let's continue. So we continue step number 4, which is H dot dl equal to I enclosed. So what we're going to state now, H phi 2 pi R. Okay, that's going to be the left hand side, similar to the one we did here. And for I enclosed, what we can observe is going to be all this current, correct? So what should be this current known as? Yes, the total current. Therefore, I can just state as what we did in our example number 1. What we observe, we state in our solve. So I should be my solution. So therefore, for H number 2 is equal to I over 2 pi R phi directions. Okay, let's say we're going to plot now our results. I'm going to plot my result now. We're going to use this result in our next discussion, so please do understand. Okay, so let's plot now our field obtained from this problem. Okay, so this is our H. Okay, so and this is our R, because we're going to plot H against R, and then we know there's going to be a boundary defining region 1 and region 2, and that defined by what? R equal to A, correct? That's good. Now for region number 1, what we can observe from our solution, that H here is proportional to the R. Okay, is R increase, H also going to increase. So therefore, it's going to be linear. So this is what we're going to represent for H inside the cylinder, and whereby for H outside the cylinder, which is here, is inversely proportional to R. So therefore, I'm going to draw that as this diagram. Okay, so therefore, that should be our H profile, the field generated by our infinite volume current. This is come from the idea of we zoom into the line current. We are closer. So now you can see when you design antenna, you have to know what's the function of the antenna. Is it for close application? For example, you want to detect the pattern of cell in a body, okay, or you're going to use as communication purposes, where usually the antenna for long distance application. So you can see, even though the structure the same, but yet the mathematics need to be adjusted according to the application that you want to use that particular problem. In this case, when you want to use close, you assume the current to be volume. When you want to use it as a far application, you assume the current to be line current. So therefore, you can solve any problem, yet when you understand what you are doing, inshallah, it's going to be easy rather than you are memorizing something that not very sure. Okay, can we do one more example here? Example number 3. Okay, example number 3. Okay, example number 3 is appear to be like this. Okay, example 3 now. Okay, just make it as title H due to surface current. Okay, H due to infinite surface current. So I'm just want to use ACL approach here, therefore I add the term infinite here. So that is the justification for me. I can use ACL in my problem solving. Okay, so I want to find H due to surface current. Okay, so let's draw the axis first so that the mathematics going to be a bit easy. So I'm going to, this is my Z, this is my X, this is my Y. So this is our X-axis, Y-axis, Z-axis. Okay, that should be our coordinate system. Then let's add our current source. So let's assume to be infinite. So I'm going to draw it to be such. Okay, that's my current. So it's located at what? At Z equal to 0. Okay, that should be what I meant. Z equal to 0 plane. And then I'm going to show that my current flowing in this particular directions. Okay, the current here, Js equal to J0 Y ampere per meter. So that should be our current source. Okay, so what the question all about? Find H in all region. Okay, that should be the question. Find H in all regions. Okay, what should be the first step here? Good. Choose coordinate system. Which one should be our selected coordinate system? Yes, it's going to be Cartesian coordinate. I'm going to explain why later on. I'm going to use Cartesian first. Then I'm going to draw my current coming out from this white paper. Okay, that should be the step I'm going to do now. So I'm going to okay, make this to be my X. Okay, Y coming out, and Z going to be in this direction. Okay, that should be in two-dimensional, and then the current going to be appear to be like this. Okay, so that should be my current. Okay, so now if you assume the current here to be a combination of line current, let's say this is one line current. So if you put another line current close to each other, that going to create what we call it surface current. Okay, I hope you can see the idea now. So I'm going to say now my surface current consists of multiple line current. So let's draw that. So this is my line current. Okay, so I put another line current close to it. So it's very close to each other, it's touching. Then this is line current. And then red line current again. So I hope you can get the idea now. So actually surface current is a combination of line current placed close to each other. Okay, that's the idea of surface current. So let's say we focus on one line current now. So what should be the field generated by this particular line current? Okay, we have done this based on our example number 1. You have infinite line current. What going to be the field produced by that line current? Good. Going to be a circle. Okay, and that circle center at that particular current. So the direction of the field is shown here. So this line current going to produce its own field, red color. Yeah, and so how about the black line current? Oh, sorry, the blue line current. Yes, it's going to produce its own field as well. Blue line current center at that particular current, and this blue line current also centered that particular current. That is going to be the corresponding field. And finally the black line current also going to produce its own field. Okay, so what you can observe here, yes, you can observe somehow that the field produced by this particular surface current is this resultant field, the black, thick black color. So that should be the field. The field generated by, because when you see that all this field showing in a uniform direction, so that pattern is a resultant pattern. So we can assume the top area of this particular surface current, the field is in which direction? Positive X, whereby the field in the bottom region of this surface current is defined as direction-wise negative X. Okay, so therefore that's the reason why we are using Cartesian coordinate, because the loop going to be rectangular, following the pattern of the field generated by the surface current. Okay, okay, good. So let's proceed now. Okay, so now I'm going to build the loop. So I'm going to redraw again, but now without all this dotted. We're going to draw blue color here. Okay, this is our current dotted. Now region of interest, one up here and one bottom here. Okay, that should be my region of interest. Okay, to make the mathematics a bit easy, so I'm going to add coordinate axis now. This is Z axis. This is our Y axis. This is our X axis. So that should be. Now I'm going to draw the loop. Okay, the loop in this case should be what here? Okay, I'm going to draw straight line. Okay, that should be one pattern. And for the bottom region also straight line, correct? Because that's the behavior of that field. And then remember the loop must be closed. So I'm going to join this line together. Okay, that should be my Amperian loop. Remember, it must pass through the appropriate location of H, then it must be closed. Okay, I'm going to define now, since it's a sensor, this particular side of my loop going to, rectangular structure going to be defined as L, and this side going to be defined as H. Okay, because we have to define dimension. This is our sensor. And remember that there's a current in here. I'm going to draw it blue color. Okay, so that should be our current. Now we're going to continue to the step number 4. Okay, step number 3, draw appropriate loop. You can see now the way I choose my loop based on the pattern I can see coming out from the source. Since the pattern of the H flat, I'm going to choose the loop to be rectangular. If the pattern of the loop is circle, I'm going to use a cylinder. So this is how you relate. The more example you do, inshallah, the clearer this step for you. So let's proceed, can we? Okay, let's go next. I'm going to solve now for this mathematics. H dot dl equal to I enclosed. Okay, that should be the mathematics. So I'm going to make it clear by dividing it to left-hand side and right-hand side so that you're going to see how those two relate together. So what we're going to do, we're going to focus for the left-hand side now. Left-hand side. Okay, so I'm going to define now my box having a number 1 at the edge here. I'm going to indicate number 2, number 3, number 4. So due to that, I'm going to set now for the left hand side. Actually, this mathematics consists of from 1 to 2 H dot dl. Okay, I'm going to continue now. I have to follow the path. 2 to 3 H dot dl. Continue yet. 3 to 4 H dot dl. Should I stop here? No. Yes, good, because it's a completely closed. So I'm going to continue 4 to 1. As you can see, starting from 1, ending at 1. Agree with the mathematics that we put earlier. So that should be what we should do. Now, let's substitute. For the H now, let's focus now. You have to be careful now here. Okay, H in this particular segment of the loop should be which H? Good, this H. Agreed? So this H must follow this H. Why? Because this H is in the upper region of our surface current. Always obey this pattern. So therefore, I'm going to set now my H here should be Hx in x directions. Okay? Hx in x directions. Okay, so now what should be my dl? Should be dx in x direction as well. Okay, now how about this particular H? From 2 to 3, you can see it consists of the top region and bottom region. For the top region, H should be always obeying this H, should be positive x, whereby in this bottom region, the H must always obeying this H, should be negative x direction. So for this H, it can be plus minus Hx x. Okay, and for the dl here should be dzz because this axis. Okay, let's continue. For this H, bottom region, yes, you can see now Hx in negative x directions. And my dl now, I'm going to choose dx in x directions. And for this one, similar Hx plus minus x directions. And this dz should be dz in z directions. Okay, so that's done. So let's now solve the mathematics now. So I'm going to solve the mathematics. Okay, so Hx, so x going to be positive. Therefore, my solution here is going to be Hx multiplied with L, correct? The length. So this term going to be 0. Why? The dot product x dot z will be 0. Okay, this one going to be plus Hx L, and this term also going to be 0. Okay, so therefore our left hand side will end with equal to 2hxl. Good. So let's continue with the right hand side now. Okay, for right hand side now, should be the current here. Okay, so therefore I'm going to say to myself should be J multiplied with what? ds or dl? Good, dl. Why? Look at the unit here. The unit, is it ampere per meter square? No. Given here ampere meter per meter. Therefore, to get ampere for the current, therefore I just need to multiply with the length. So therefore, what should be my solution here? Okay, the length. So the dl here should be dx. Okay, the sample here should be dx. Okay, therefore the limit 0 to L. So it should be J naught multiplied with L. And when we substitute together, we're going to see the Hx equal to J naught divided with 2. Okay, so now let's conclude our solution now. So this is the magnitude. The magnitude is what we observe. This is Hx, this is Hx. So now what we're going to define now, for z greater than 0, so that's indicate where upper region, our H top going to be what? Going to be the Hx, which is J naught over 2. And what should be the direction of our field here? Good, positive x. And for z smaller than 0, the H bottom, you can see from the diagram what should be the solution now. Because in this direction, good, magnitude wise the same, J naught over 2, but the direction negative x. So therefore that should be the corresponding field that we can solve for infinite surface current. So a bit difficult first, but inshallah when you go through it slowly, I believe you can see it's not that difficult. So let's prove whether our solution is correct or wrong. Okay, because I like to do that when I solve my problem, always with that attitude verification. Okay, so for infinite surface current, so this is general statement, yeah, for infinite surface current, H, okay, is always defined as this mathematic half Js cross An. Okay, that should be our standard formula that you can try to memorize. If you don't want to use this approach that I show you, you can just memorize this formula. Inshallah, you're going to get the same solution. Shall we prove it? Okay, let's prove now. Yeah. Okay, so let's do for first region now. Yeah, for z greater than 0. Okay, let's do that. Okay, for this region. Okay, what should be our formula? Okay, half, that's done. Js equal to what? Whatever field given here, J naught in y direction, correct? Cross with An. An must be always away from the current, so An is going to be as such for region z greater than 0. So this An equal to what in this particular diagram? Good, positive z. So now, if you multiply y cross z, okay, what should be the solution? Good, x. So what you're going to have? J naught over 2x. Is it same as what we have obtained before? Yes. Okay, therefore this formula can be used. Okay, let's prove further. Some of you still don't appreciate it, so let's do it for z smaller than 0 now. I'm going to use a different color so that you can see the difference. Okay, so half, because the formula state half, I'm going to just copy half. Then the Js, whatever current given in the problem, J naught y direction, cross AN. Now AN is away from the current, showing downward, should be negative Z. So when you do the mathematics, inshallah, you're going to end with J naught over 2 with negative X. Okay, so therefore, again, agreed with what we have proven earlier using quite lengthy approach of ACL. So let's case in the problem, they do not ask you to prove, then you can use this standard formula for your infinite surface current. I think it's similar as what you have seen in our electrostatic. For infinite surface charge, what is our E? E should be equal to rho S over 2 AN. I think epsilon, 2 epsilon AN. So it's a similar idea that you have seen before in electrostatic. So this is in magnetostatic. Okay, so alhamdulillah, we have completed 3 examples related to Ampere's circuital law. I'm really hoping that for you to see the steps that you should follow through when you want to use ACL in your problem solving. Yeah? So the step is matter. So just understand the step. Whatever structure given to you, if you understand the step, inshallah, it's not that difficult. Okay, I'm going to do another example maybe in my tutorial sessions regarding solenoid, because we have done solenoid in our example in I think in Coulomb's law. So therefore I'm going to in Biot-Savart law. So I'm going to do solenoid problem in my coming tutorial video. Okay, with that, thank you very much. Assalamualaikum warahmatullahi ta'ala wabarakatuh.